Okay, this is Module 3, Video E. We're going to be talking about model selection in linear regression. So in the last video, we ran this model using the Statsmodels package. We got all our model statistics and also the coefficients for our variables. And if all we care about is getting accurate predictions, we're done here. We have our model, we can use it for predictions. However, often when we're making models, we're not just interested in their predictive power, we're also interested in making the model simple and interpretable. So that's what we focus on in model selection. So the first thing we're going to look at as far as simplifying the model is we want to see if any of the predictors we're using are insignificant or, just kind of unnecessary, not contributing to the model. So to look at that, we're going to look right here in this column. Well, that didn't really highlight a column very well. Right here, our column that gives our p-values. So our p-values show how significant our predictors are. What the p-value actually statistically is it is giving you the probability that you would see this coefficient or a more extreme coefficient if the correlation were only due to chance. So kind of what that is if you put in two variables into a linear regression model that have absolutely no correlation with each other, like they're not related at all, the model will still run and give you a coefficient. It's going to give a coefficient for every single variable. But just because that variable has a coefficient doesn't mean that the variable is doing anything to help predict. So that's what this is looking at. It's saying, okay, if these were just like completely unrelated variables, what is the chance that you would get this coefficient? So if our p-value is high, that means there is a high likelihood that this predictor and the coefficient associated with it is really just due to random noise and isn't because of any correlation. So generally in statistics, we'll pick a significance value of 0.5, occasionally 0.1, and if our p-values aren't below that, we say this isn't significant and we kick it out. So that's the first step we're going to do. So if we look through here, if we're using a 0.5 significance, in that case, Zn is not significant, Indus is not significant, and neither is age. So just to start here, we're going to take Zn, Indus, and age out of our model. So I'm going to go down here. I'm going to, let's see, ZM, Indus. Oh, I'd accidentally selected Crim, but Crim is actually fine. It can stay. So we're going to drop Zn, age, and Indus from X, and I'll make a new data frame called X2. And then I'm going to go back and fit the model on this X2 data frame. So as before, I'll add the intercept, call it x-intercept2. Then I'm going to fit the model, call it model2, print out my summary statistics. So here are my summary statistics. If we're looking at that r-squared value, which is showing how much variance our model is explaining, before, I believe, let's see, it was 0.790, and now it is 0.789. So we've dropped 3 variables, but we've lost very, very little predictive power in our model. So that's super good. We have a more simple model that is pretty much just as accurate, win-win on both sides. We could stop here, but if we're really trying to get an interpretable model, there's one more thing we want to look at, and that is multicollinearity. If we go down to the notes here, we have a note, and it's not quite an error, but yeah, a note that says the condition number is large. This might indicate that there are strong multicollinearity or other numerical problems. So What multicollinearity is it is when two of your predictor variables have a high correlation with each other. So these two predictors that you're using are kind of measuring the same thing. So for example, if we were looking at data about a person, perhaps if we had charted the person's weight and then also their pant size, we're trying to predict some other thing based on that, maybe, how much they need to eat in a day, we might find that weight and pant size are both kind of telling us the same thing. Now, of course, it's not telling you exactly the same thing, but those would be two predictor variables that have a correlation to each other. Now, on the surface, that doesn't really seem like a bad thing. We're just getting more data. And if we only care about our predictions, we don't need to care about multicollinearity. However, where there are issues is when we're looking at the interpretability of our model. If we have predictor variables with high multicollinearity, it can kind of mess up our coefficients and the meaning of our coefficients. So if two predictor variables are measuring the same thing or very close to the same thing, you get this interesting situation in the model where if I call these variables A and B, I get pretty much the same result if I say 2A plus 4B as if I say 3A plus 3B. Because, if they're pretty much the same thing, you can kind of put the coefficients any way you want as long as the sum is the same. And so because of that, we get this weird situation where our coefficients are no longer meaningful. They're useful as far as predictions, but they're no longer meaningful to us, and we can no longer say, oh, for every increase in A, the response variable will increase by this much, just because they're not meaningful coefficients anymore. If this is something you're interested in looking more into, you can Google multicollinearity, you can watch videos about it. It's really interesting. But for now, that's the basic idea. If we want our model to be interpretable, we don't want multicollinearity. So what we're going to do is let's go back and run a correlation matrix again and see which of our variables might be causing problems. So if I run this, I can see right away that I have a couple variables or predictors that are very similar to each other. We have tax and rad right here are highly correlated. And also right here we can see that tax and rad are both super correlated with crim. And then we can also see that dis and nox are really correlated to each other. So what we probably want to do is we want to drop either dis or nox, and we should probably drop at least tax or rad, and maybe also crim, but I'd say we should at least drop tax or rad. So there's a couple different ways that you can choose which one to drop. Some people are just going to look at, okay, what can I drop that will still give me the best predictions? I think it's also really good to look at what things are actually measuring though. So for example, in this case, NOx is measuring the nitric acid concentrations. So I believe that's a pollutant. So it's looking at how polluted it is. And let's say a NOx was related to DIS. DIS is measuring the weighted distance to 5 Boston employment centers. So that's interesting. The distance to the employment center has a strong negative correlation to the amount of pollutants in there. So the further you are from an employment center, the less polluted things are. Shocker. I think it's really interesting actually that those two are pretty much measuring the same thing. At least as far as this data set is concerned. And then rad and tax. So let's see, rad is the index of accessibility to radial highways, and tax is the full value property tax per $10,000. So in this case, so I need to choose to eliminate one of each of these. I'm going to say let's eliminate NOx. I can just see that being something a little hard to measure. Obviously they measured it for this data set, but if you're going to go on and, make predictions in the future, knowing how far you are from an employment center is probably easier than getting like an environmental study to figure out the nitric acid concentration. And then rad and tax. These are both interesting. I'm going to say for the sake of this, I'm a little more interested in rad, how close you are to radial highways. So let's drop tax. So that's what we're doing right here. We're dropping NOx and we're dropping tax. Let's run that model. And we now see that our R squared, it has dropped a little bit this time. Not a ton. It was at 0.789. Now it is at 0.771. So if you're really worried about the predictive power of your model, maybe you're not okay with this, and maybe you go back and say, okay, well, what if I dropped dis instead of NOx? Or what if I dropped rad instead of tax? Or maybe you just say, you know what, I don't really care about interpretability, I'm just going to leave in the multicollinear variables because they give me better predictions. These are all judgments you need to make, and it's really going to depend on what you're using this model for. However, overall, I'd say this is pretty good. We've simplified our model down, so we now just have 1, 2, 3, 4, 5, 6, 7, 8 predictor variables. That's still kind of a lot, but less than we started with. And we still have a fairly good R squared. So yeah, that is the idea of model selection. And I'll see you in the next video to wrap up this section and talk about actually making predictions with our model.